Helicopters and drones are interesting flying machines. Helicopters were invented in the late 1930s, and drones were invented in the 1980s and 90s. Drones have recently become popular for civilian use because they can be used by the public for racing and photography. But they've always been used by the military for surveillance. Both helicopters and drones operate on the same scientific principle. They need to generate enough lift that they can be able to fly, because they have to generate a lot of lift to be able to support all their weight. I had three problems for my experiment. First was that the RPMs of a drone's blades change when it hovers at 1.52 meters, 3.05 meters, and 6.1 meters above the ground. My second problem was, while adding 433 grams of weight to a drone increases the amount of RPMs as it hovers at 1.52 meters, 3.05 meters, and 6.1 meters above the ground. My third problem was, well, the RPMs of the blades of a toy helicopter increase when it weighs 40 grams, 42 grams, 48 grams, and 54 grams. My hypotheses for these experiments were, for the first experiment, I thought that the drone would have the most RPMs at 6.1 meters and the least at 1.52 meters. For the second experiment, my hypothesis was that the drone's blades RPM would increase when it had the weights added. For the third problem, my hypothesis was that the toy helicopter's blades would have the most RPMs when it had weights added. My procedure for the first experiment was, I purchased a tachometer, I borrowed a photography drone, and I used a 433 gram weight on hand. I had an assistant fly the drone at 1.52 meters above the ground and another assistant using the tachometer. The first tachometer that we tried was a digital tachometer, and it was very hard to operate. The second tachometer that we used was an audio tachometer, which did not give reliable results. We settled on using an optical tachometer, which blinks really fast to help measure the RPM. We took the tachometer's reading and recorded the results with 5 repetitions. Then we repeated this process when the drone hovered at 3.05 meters and 6.1 meters. For this experiment, the variable was the height and the constant was the weight. For my second experiment, I used all the materials for the first experiment in Scotch tape. I added 433 grams of weight to the drone and repeated the first procedure. I compared the results to those of the first experiment. The variable was the weight and the constant was the heights. For my third experiment, I purchased a toy helicopter, used the tachometer from the first experiment, a craft stick, 4 pennies, and a hot glue gun. To count the RPMs, I used a remote control and made the helicopter's blade spin faster and faster until it would almost start to lift off the ground. That was when one of my assistants would take the tachometer and count the RPMs of the blades. We recorded the results of this with 5 repetitions. Then we hot glued a craft stick to the base of the helicopter to bring the weight, which brought the weight up to 42 grams. The original weight was 40 grams. And then we tested this the same way with 5 repetitions. Then we hot glued 2 pennies to either side of the craft. We hot glued 2 pennies to the craft stick with 1 on each side, which brought the weight up to 48 grams and tested it the same way as I mentioned before. Then we hot glued 2 more pennies the same way, which brought the weight up to 54 grams, and we tested it again. My results for the first experiment were that the RPMs were the least at 3.05 meters. The RPMs at 1.52 meters were, on average, 3,341. The RPM average at 3.05 meters was 3,200. The RPM average at 6.1 meters was 3,477. For my second experiment, the RPM did increase when I added weights. The RPM with weights at 1.52 meters was 3,362 on average. At 3.05 meters, the average RPM was 3,422. The RPM at 6.1 meters was 3,513 on average. For my third experiment, the RPM before takeoff increased with weights added. Without weights, which would be 40 grams, the average RPM was 2,211. When it weighed 42 grams, the average RPM was 2,266. At 48 grams, the average RPM was 2,277. At 54 grams, the average RPM was 2,314. My conclusions were, for the first experiment, my hypothesis was not supported because the RPMs were the least at 3.05 meter. I had predicted that they would be the least at 1.52 meters, but they were actually the least at this height. One possible reason for this could have been the air turbulence patterns, or it could have been the differences in wind speeds, considering we were doing it behind a building. For my second experiment, my hypothesis was supported because adding weights did increase the drone's RPM. And for the third experiment, my hypothesis was also supported because adding weights did increase the helicopter's blade's RPM. Any questions?
How did you come up with the heights that you took your readings on the drone? You had like 1.5 something or another meters, and how'd you come up with those?
Well, we converted the heights of feet to meters. I believe it was 10 feet and 20 feet and 50 feet.
And can you explain more about how you use that tachometer to count revolutions per minute?
Well, you turn it on by pressing a button, and then you look through this little thing, and you turn the dial until it looks like the blades of the drone or the helicopter stop moving, and then when it stops moving, then that's the reading. Like for example, if it stopped here, then it would be 3,188 RPMs. Thank you.
I have a question for you also.
Okay.
Okay, if you were using a drone in an emergency situation where you had to deliver, say, a medicine package to from where you were at to someone over the hill,
Yes.
and the drone had a camera on it so you could see what was going on, and you knew that the package was going to weigh, some significant amount, say 1 or 2 pounds or maybe 10 pounds. I would think that you'd want to design that drone to have to not just have enough, to have enough power and capacity beyond just what it takes to fly itself. That you'd have to design it to carry the heavy load.
Yes,
although you wouldn't be using that all the time.
Yeah, you'd have to design it so it'd be capable of lifting more than just its weight.
Right.
All right. Thank you.